Good morning everyone. Myself B. Kashinath, Senior Lecturer in Electronics and Communication Engineering, presently working at Government Polytechnic Sangareddy. Government Polytechnic Sangareddy. I am going to teach the subject of electronic measuring instruments, which is in third year, 5th semester. Third year, 5th semester, electronic measuring instruments. And the topic which we are going to discuss today is the test instruments, and the subtopic is spectrum analyzer, and the subject code of this electronic measuring instruments is 18EC504EMI, and it is comes under the elective subject of C18 curriculum of State Board of Technical Education, Telangana State. So we are mentioning it as in bracket E, and it is the first option, so it is A. So finally it is 18EC504EMI elective A. So the subject is electronic measuring instruments, and the topic is the final chapter. That is test instruments. In that one subtopic which we are going to discuss today is the spectrum analyzer. So in the previous class we have learned about the uh, total harmonic distortion meter or distortion factor meter. uh, uh, in that we are measuring the total harmonic distortion by using the Wien bridge method. So distortion factor meter with the use of Wien bridge method, which will act as a rejection amplifier, which will suppress the fundamental component of your input signal, and which will pass all the harmonics of your input signal. So in that block diagram we have explained about the that is, you will be having the input, and you will be having the impedance converter. So main parts of the distortion factor meters are impedance converter, which is applied to your input, and second part is your rejection amplifier, third part is metering circuit, fourth part is power supply. So and distortion factor meter has two modes of operation. When the switch is in position of voltmeter, it will normally works as the AC voltmeter, which will be used for measurement of your AC voltmeter readings, or you can check the gain measurements of input between the output and input. When the switch is in position 2, then it is connected to distortion position. Then you can adjust your distortion levels by using the sensitivity control. That sensitivity control will be having the total 50 dB total 50 dB attenuation in terms of the 10 dB steps. So you can choose different types, different amount of distortion that is applied to the impedance converter. Impedance converter is a low noise, high input impedance, such that the source impedance will not affect the distortion factor in meter instrument. So that is the main advantage of the impedance converter. So it is 1:1 converter having the low noise and high input impedance. That input impedance will not cause any loading effect on whatever may be the input impedance of your source impedance. Then the output from the impedance converter will goes to the rejection amplifier. Rejection amplifier will consist of three parts. First one is pre-amplifier, which will amplifies the signal from the impedance converter to a certain level, so that your Wien bridge amplifier, Wien bridge section of the rejection amplifier, which will be acting like a notch filter, which will pass the it will be on resonance to the your fundamental frequency, so that frequency will be suppressed, and removing all the harmonics will be passed through your rejection amplifier. That will be amplified by the post amplifier. Then it is given to the post attenuator section, which will attenuates the signal such that signals will be, all the harmonic signals will be given to the uh, metering circuit. So the metering circuit will be able to that is calibrated in terms of the a direct distortion in percentage of total harmonic distortion. So it is calibrated in terms of RMS volts RMS scale, such that it will give the total harmonic distortion. And power supply is giving the supply to all the components within the circuit. And the main advantage of this one is the selectivity requirement will be less, and it will give the total harmonic distortion as a percentage of your input. But the main disadvantage of distortion factor meter is it will not give the individual component distortion, it will only give the total harmonic distortion. So that is the previous topic that we have learned yesterday, that is the distortion factor meter. And today we are going to discuss about the spectrum analyzer. So on completion of this period you will be able to know about this super heterodyne spectrum analyzer. Anyway, digital spectrum analyzer is not in our syllabus, so we are not going to discuss that one. Only spectrum analyzer using the super heterodyne swept frequency technique. So actually, what is frequency spectrum? So what is frequency spectrum? What is spectrum analyzer? When we are going for what is spectrum analyzer, first we have to know about the what is spectrum. So when we are talking about the spectrum, actually we are not dealing with the timing analysis, we are dealing with the frequency analysis. So first we have to know about the frequency spectrum. Frequency spectrum means here what we are doing is in normally in all the cases in electronics, what we are going to measure, we are measuring the signal amplitude with respect to time. That is, in your x-axis you are having the time, that as the time varying, we are checking on the y-axis the gain or amplitude of your signal. So on the y-axis you will be having the amplitude, whereas in x-axis you will be having the time. So the time varying signal we are measuring the amplitude. But in case of frequency spectrum, it is not like that. It is with respect to time the amplitude, but here we are measuring the amplitude or electrical characteristics uh, of any waveform. That is, we are the distribution of the frequency. So on the x-axis we are taking not taking the time period, but we are taking the distribution of your frequency component. That is, on x-axis you will be having the frequency, on the y-axis you will be having the amplitude of the signal. So the frequency spectrum is known as, we know that the frequency components amplitude. So amplitude may be your voltage or power. So we are drawing a relationship between the old frequency components amplitude, that is voltage or power, versus the frequency, that is called frequency spectrum. So here what we are doing, we are the distribution of the frequency component of the electrical signal plotted as a graph, that we are calling it as frequency spectrum. So on the y-axis you will be having the amplitude, that may be your voltage or power. On the x-axis you will be having the frequency. It is called the frequency spectrum of the signal. And the instrument providing this frequency spectrum, or the instrument providing this frequency domain view, we are calling it as spectrum analyzer. So the instrument which is providing, or the instrument which is giving this frequency domain view of the frequency spectrum is known as spectrum analyzer. So what is spectrum analyzer means? It is the instrument providing the frequency domain view of your signal. That is, on x-axis you will be having the frequency, and y-axis you will be having the amplitude of your electrical signal, that is either voltage or power. So spectrum analyzer provides the calibrated graphical display. So it provides the calibrated graphical display on its cathode ray tube. So spectrum analyzer provides the calibrated graphical display on its cathode ray tube with frequency on the horizontal axis, that is frequency on the x-axis, and amplitude on the vertical axis. Amplitude means voltage on the vertical axis. So the instrument which is providing the frequency domain view is the spectrum analyzer, which will provides the calibrated graphical display on the CRT. So spectrum analyzer is an instrument which will provides the calibrated graphical display on its CRT, where on x-axis you will be having the frequency, on the y-axis, on the vertical axis you will be having the amplitude, and the spectrum will look like as in the case of CRO or with respect to time domain axis you will be having the continuous sinusoidal signals, but in case of this frequency spectrum you don't have like continuous time varying signal, but you will be having at discrete frequencies you will be having the amplitude that will be shown as vertical lines, so the vertical line amplitude will be at that frequency. You may know that that is the amount of voltage or amplitude at that level. So simply take, if you are having at second year level analog communication, you are having amplitude modulation. So when we are drawing the amplitude modulation spectrum, that is voltage on y-axis and frequency on x-axis, so you will be having the three frequencies, that is fc, fc plus fm, fc minus fm. That is, fc is the carrier frequency, fm is the modulated frequency, so modulating frequency. So you will be having only three components in the frequency spectrum of AM, where you will be having three voltage spikes of vertical lines. One is at fc, one is at fc plus fm, and third one is at fc minus fm, and that amplitudes you can measure. So it displayed as vertical lines against xy coordinates. So here the display of the frequency spectrum is looking like it displayed as vertical lines, as you have seen of AM spectrum. So it displayed as vertical lines against the xy coordinates of the sinusoidal components. So in time domain axis you are seeing the complete time varying signal with a continuous variations, but in case of the spectrum analyzer or frequency and spectrum, the instrument which is providing the frequency spectrum is the spectrum analyzer. In that, display is vertical lines against the xy coordinates as opposed to the sinusoidal components of which the input signal is composed. So your input signal is mainly composed of the sinusoidal signal, but your frequency spectrum will look like only the vertical lines at different frequencies. So basic principle of operation of the spectrum analyzer, it uses two types of techniques. So that two techniques are, first one is parallel filter bank technique and second one is swept frequency technique. So spectrum analyzer uses two techniques, one is parallel filter bank and second one is swept frequency technique. So in case of parallel filter bank analyzers, so you will be having the many number of filters that are parallel, means one after the other. So in that one, what we are doing is the entire frequency range of your input will be covered by the series of filters. So as the name indicates, parallel filter bank, so your entire input frequency range is covered by the series of filters whose control frequency and bandwidth are so selected that they are overlap with each other. So no frequency is uncovered, so all the frequencies should be covered. So that what we are doing is total frequency range is covered by the we are putting series of filters, so whose central frequencies, so series of filters will be having whose central control frequencies and bandwidth are selected so such that they overlap with each other, so that entire frequency range of your input range is covered by this parallel filter bank techniques. And the second technique that we are using particularly at large frequencies, that consider the radio frequencies and microwave frequencies, we cannot do the all the filtering action, means all the filters we cannot place, then it will be very costly effect. So that's where we are using the this swept technique, which is used for perform for a wide band. So it is used for wide band narrow resolution analysis. So when we are going for the wide band narrow resolution analysis, we are going for the swept technique, so which is mostly used at RF or microwave signals, radio frequency and microwave signals. We are going for the swept technique. For small frequencies where the input is having only audio frequency like that, we are going for the parallel filter bank techniques, where the we are putting the series of filters, the entire frequency range is covered by the series of filters whose control frequencies and bandwidth are selected that they overlap with each other in parallel filter bank technique analyzers. But in case of swept technique, it is performed at wideband narrow resolution analysis. It is done at RF radio frequency and microwave signal levels. Uh, Different types of spectrum analyzers. We are having the swept frequency technique spectrum analyzer, digital spectrum analyzer, or you can go for the hybrid spectrum analyzer or vector spectrum analyzers. There are the different types of spectrum analyzers. You can take a screenshot or you can note it down. So in our syllabus we are having the this swept super heterodyne spectrum analyzer. In our syllabus we are having the swept super heterodyne spectrum analyzer. This we will discuss. So this may come in your exam also. This is very much important. You can draw this diagram. So this is the block diagram of the swept stripe super heterodyne spectrum analyzer. So in this one, basically this spectrum analyzer consists of the narrow band super heterodyne receiver. So the top part you are seeing that, so it is a super heterodyne receiver, and you will be having one CRO. So swept super heterodyne spectrum analyzer consists of two main parts. One is your narrow band super heterodyne receiver, and second part is CRO. And your this sawtooth generator. So in the bottom side you can see the sawtooth generator, which will provide the sawtooth voltage to horizontal deflection amplifier. So in the bottom part you can see the sawtooth generator or sweep generator, or you can call it as sawtooth or sweep generator, as you have already know about the CRO. In CRO you will be having the vertical deflection amplifier, which will run the y-axis, and x-axis will be run by the horizontal deflection amplifier. So this horizontal deflection amplifier will be uh, uh, the voltage which will drive this horizontal deflection amplifier will be provided by this sweep generator or sawtooth generator. So which will provide the voltage which will drive the horizontal amplifier or horizontal axis element of the CRO CRT tube. And this sweep voltage is frequency controlled element of the voltage tuned oscillator. So this sweep generator, or I can call it as sweep or sawtooth, you can write any thing. So this sweep or sawtooth voltage generator is frequency controlled element of the voltage tuned oscillator. And this voltage tuned oscillator having can vary the frequency from f minimum to f maximum, and it can also work as a local oscillator to the super heterodyne type receiver. In that one, at the mixer section you can have the local oscillator. So this voltage tunable oscillator will be working as local oscillator, and it is also providing the frequency controlled element of the voltage tuned oscillator, is giving the driving this sweep generator. So now the operation of this one is whatever the signal input frequency fs, that is RF signal under investigation. So RF signal under investigation is applied to the input of the mixer. So whatever the input signal, or that is the signal under investigation of your known RF signal, is applied to the input of the mixer. And the another input to the mixer, as I already said, is your uh, uh, frequency coming from the voltage tuned oscillator. So the another input is the output of the local oscillator, that is coming from the voltage tuned oscillator. As the voltage tuned oscillator is sweeping from f minimum to f maximum of its frequency band at a linear recurring rate. So this f minimum to f max of your local oscillator, which is nothing but voltage tunable oscillator, which varies at a linear recurring rate, means it is varying not like a non-linear, so it has to vary like linear, and it is at recurring rate. So it is varying at a recurring rate. So whenever this f minimum to f max is varying at a linear recurring rate, so it has to beat with your input frequency. It has to beat with your input frequency. So it beats the frequency component of the input signal, and which will produces the intermediate frequency. So as voltage tuned oscillator frequency is varying from f minimum to f max, whenever it beats with your input frequency, then it will generate the intermediate frequency. That is, whenever a frequency component of your input is met during its sweep from f minimum to f max, that frequency component and your voltage tuned oscillator frequency beats together. So that when the sweep action is taking place between the voltage tuned oscillator from f minimum to f max, at one of the frequency of the input, it will beats with the voltage tuned oscillator, which will generate the intermediate frequency. So both the this input and local oscillator beats and will produce together a difference frequency known as intermediate frequency. So this intermediate frequency corresponding to the component is amplified and detected if necessary, and then it is applied to the vertical deflection plates of the CRO, thus by producing a display of the amplitude versus frequency, thus by display of the amplitude versus frequency. So again I am explaining. So what happens in this, in swept super heterodyne receiver spectrum analyzer, you will be having the two sections. One section is super heterodyne receiver, second one is your CRO. To the CRO's horizontal deflection amplifier, uh, the driving voltage is given by the sweep generator or sawtooth voltage generator, and the frequency component of this sweep generator is coming from the voltage tunable oscillator, which will sweep from f minimum to f maximum, and the RF signal under consideration is given as input to the mixer. Another input to the mixer is your local oscillator, which is nothing but the voltage tuned oscillator. As the voltage tuned oscillator frequency is varying from f minimum to f maximum, it will beats with your input frequency at a certain frequency, that is, this your f minimum to f maximum is varying at a linear recurring rate. So whenever there is a match of this two frequencies, it will produce the difference frequencies known as the IF amplifier. IF frequency, so that is almost 100 kilohertz, so that will be amplified by the IF amplifier. It will be detected if necessary, and it will be applied to the vertical deflection amplifier of your CRT, then it will gives the visual display on the CRO. So that is the um, block diagram explanation of your swept super heterodyne spectrum analyzer. So sweep generator or sawtooth generator produces the linear ramp, which will drives your horizontal amplifier of your CRO, and which will also drives the your voltage tunable oscillator. And the voltage tunable oscillator, its frequency depends on the magnitude of the ramp signal. So The voltage tunable oscillator frequencies depend on the ramp signal, that is your sawtooth wave signal or sweep generator signal, and this generates the frequency which shifts from f minimum to f maximum. So for that variation of the frequency, we are using the varicap diode connected as part of the LC tank circuit to generate the sweep frequency from f minimum to f max. And the mixer, which is a nonlinear circuit or device that accepts two inputs that are two different frequency at its input, two different frequencies, so that frequencies are f0 present at the output frequencies ranging from f0 plus fs to f0 minus fs. So it will beats to a certain frequency, then it will produces the intermediate frequency, and the resolution can be increased by using more down converters in the mixer section. So whenever the both the input section and the voltage tunable oscillator frequency beats together, it will provide the intermediate frequency. So that intermediate frequency is tuned to 100 kilohertz. By that, sensitivity will be improved and it will be further amplified and given to the detector will detects the that is converts the IF amplifier input to DC voltage and apply this DC voltage to the vertical plates of your CRT, vertical plates of your cathode ray tube. If the input signal frequency, suppose if you are taking the input signal frequency fs as the addition of your sweep frequencies, that is maximum minimum divided by 2, then your fs will appear at the center of the screen. So based on your signal frequency and this f minimum to f max divided by 2, then your signal frequency will appear at the center of the screen on the CRT. And the so the swept sweep super as analyzer controls the mainly it will say frequency tuning control of the analyzer and selecting of the display frequency, and this sets the position of the frequency component anywhere on the display and sets the negative marker anywhere on the display. The basic the features of this swept super heterodyne spectrum analyzer, the controls frequency tuning control and selecting of the display frequency and the setting the position of the frequency component anywhere on the display and sets the negative marker on anywhere on the display. So and second control, frequency span by division control, which will be sets the displayed frequency range. So suppose if you are taking 1 megahertz selection, then each horizontal line will be 1 megahertz. If you are taking the frequency span for division as 10 megahertz, then each horizontal line will be 10 megahertz. And third control is reference level control, so which will be used to adjust the amplitude of the main signal. And the specifications of this super heterodyne spectrum analyzer are the frequency range that it can measure the spectrum from 20 Hz to 40 megahertz, so that is the audio frequency to radio frequencies, and 100 Hz to 22 megahertz. So this is audio frequency, and first one is radio frequency, and you will be having the resolution bandwidth. So it is the smallest signal separation. So for frequency range from 20 Hz to 40 megahertz, the resolution bandwidth is 3 Hz at low end, and at high end it is 30 kilohertz at high end. So that is the smallest signal separation between the two frequency components. For a frequency range of 20 Hz to 40 Hz, this one will be 3 Hz at low end and 30 kilohertz at high end. And the sensitivity of minus 120 dB to 3 dB, and minimum signal that can be observed and narrowest resolution bandwidth gives highest sensitivity. So for having the highest sensitivity, go for the narrowest resolution bandwidth. And signal amplitude range is from 3 millivolts to 30 volts. Signal amplitude range is 3 volts to 30 3 millivolts to 30 volts, and the dynamic range that can be offered by this spectrum analyzer is 80 dB. So that dynamic range is the difference between the maximum and minimum and maximum signal levels. And main advantages of this one is it, it has ability to give high frequency range in the digital analyzers, that is from 0 to 22 gigahertz, and you can have higher sensitivity compared to swept tunable radio frequency receiver spectrum analyzer due to IF amplifier introduction. And detector performance improve as it has to operate at 1 IF, that is detector only has to detect the only intermediate frequency of 100 kilohertz, so it improves the detector performance. What are disadvantages here? It measures only steady state signals. When the signal is not steady, it will not measure the frequency spectrum, and relative phases of frequencies are not displayed, and measurement time is long, so 10 to 100 times than the digital, and less resolution compared to digital, and oscillator frequency is frequency modulated by random noise results in phase noise. These are the disadvantages of your super heterodyne spectrum analyzer. You can note down these ones. Actually you can note advantages then disadvantages. You can note down the first advantages. So it provides a high frequency range, higher sensitivity compared to TRF receiver, and detector performance is improved as it has to operate only at one frequency, that is one IF frequency of 100 kilohertz. And the disadvantages are it can only measure the steady state signal, relative phases of frequencies are not displayed, and measurement time is long, that is 10 to 100 times in the digital techniques, and less resolution compared to digital techniques, and oscillator frequency is phase modulated by external random noise, which will result in the phase noise. Applications. So it can be used for analyzing the signals of various frequency ranges from 0 to 22 gigahertz. It can we can examine the either pure sinusoidal with or without modulation, and purity of the signals, and you can check the amplitude modulation, frequency modulation, harmonic distortion, pulse modulation, asymmetrical spectrum, and you can also check the intermodulation content. So these are the various applications of the spectrum analyzer. You can check the you can examine the pure sinusoid with or without modulation, and you can check the purity of the signal, and you can examine the amplitude modulation, frequency modulation, and you can examine the harmonic distortion and various harmonic components, and you can also check the asymmetrical spectrum. You can examine the pulse modulation, and you can examine the intermodulation content. So this is how it would look like. So on the summary, we have learned about the working, construction and applications, advantages and disadvantages, and specifications of the Swift super heterodyne spectrum analyzer. What are the frequently asked questions? Applications. You can also ask advantages and disadvantages, or you can ask what is spectrum analyzer, and explain the principal operation of spectrum analyzer, that you can write this block diagram with explanation of the swept super heterodyne spectrum analyzer. Thank you very much.